Okay, so in 6.6, we are factoring polynomials. So we're going to find remainders and evaluate the functions using the remainder theorem. We're going to factor polynomials using the rational root theorem, the factor theorem, and synthetic division. And then we're going to, the last one, select polynomials using special patterns. Okay, so that'll be day 2 for sure. But I want to look at the general forms of all these different equations that you guys have learned. So the first one is the general form here of linear functions. Okay, is that f of x or y equals mx plus b. Okay, for the quadratic function, the general form is ax squared plus bx plus c. Okay, so it always has a square in it. Okay, it has a variable that's squared. For a polynomial, okay, p of x, okay, is we have a coefficient in front and we have a variable, or we have an exponent of n, and then it's n minus 1 and then n minus 2, and it goes down until, well, this should be, so there's just 1 here, right? We don't write it. And then this is a to the power of 0. This is the constant.
What?
Okay, so what we're kind of getting at here is the polynomial. Anything above a power of 2 is a polynomial function. It could have a power of 16. It's a polynomial function. Okay, so it's just saying whatever n is, and then it has to be in descending order. So if this was 7, and then we have 6, 5, 4, 3, 2, 1, constant. Okay, so anything over an x to the power of 2 is a polynomial.
So that's just a confusing way of writing what we've been doing.
Yes, it is. All right. So that's just kind of like, again, to help us think like, all right, if the highest exponent I have is x to the power of 1, it's linear. If I have x to the power of 2 or whatever variable, it's quadratic. If it's anything greater than that, it's a polynomial function. Okay, so then the remainder theorem. If a polynomial, so this, we would write that as p of x, is divided by a binomial, so then we have x minus a, the remainder is p of a. The remainder is p of a. So let's actually try this out. It'll make more sense once we see it. So let me clear this up and move it up here. We'll keep the remainder theorem. So example 1 says find the remainder when x to the 4th minus 6x cubed minus x squared plus 2x plus 7 is divided by x minus 1. So notice we're looking for this binomial pattern, x minus a. So what is our a here? 1. Okay, so a equals 1. All right, and it says find the remainder. Right, we're not actually solving it, we're just finding the remainder. So we're going to, we do not actually, because this remainder theorem says if a polynomial is divided by a binomial like this, which is what's happening, we have this polynomial, we're dividing it by this binomial x minus a, the remainder is p of a. So our a here is 1. So we're going to solve p of 1. Instead of solving the whole thing, we're going to plug 1 in for all of our x values and get our remainder that way. Well, let's do it, and then you can tell me what you think. It depends on the number sometimes. Like 1 is a really nice one. So this is going to be 1 to the 4th minus 6 times 1. I almost wrote x. Cubed minus 1 squared plus 2 times 1 plus 7. Again, 1 is a nice number. So 1 to the 4th is 1. 1 to the 3rd is 1. So negative 6 times 1, negative 6. 1 squared is 1. So minus 1. Plus 2 times 1 is, and then plus 7. So 1 minus 6, negative 5, minus 1, negative 6, plus 2, negative 4, plus 7. positive 3. Okay, and you could do it a little bit differently, but P of 1 equals 3. So that means our remainder is 3. That's really the answer to our question because it said find the remainder. So it kind of is up to you. Like, I mean, when you're given this problem, unless it says use the remainder theorem, you could also do like the synthetic division. So we would have, let's see, 1, negative 6, negative 1, 2, 7, divided by 1. What's your question, bud?
Okay, so
I'm just saying.
doing, let's say, like hypothetically, that was like a 3x minus 9 instead. Instead of x minus 1. When you divided it, and then you use that thing, you have to divide all of them but the remainder. So if it's 3x minus 1, or 3x minus 9, you divide it by 3, it wouldn't affect your remainder. So you could just divide it by that to get it to like this type of thing. And go through it and still get the same remainder.
Theoretically, yes. Yeah, theoretically.
So it doesn't change the remainder when you do that. So for like this type of problem, if you have like an or not an exponent, a coefficient in front of the x, and then like a number that's divisible by subtracted, you get the same remainder.
Yeah, I have not tried that, but yeah, theoretically it should. So we might have to try one. Go back and try the one from the problem.
I have a question.
Yes.
Sorry, I didn't know that. But so why? So for example A, you got 5 pi.
Okay, so let's try the synthetic division here to make sure we get the same remainder for this problem. So 1 times 1 is 1, negative 6 plus 1 is negative 5, 1 times negative 5 is negative 5, negative 1 plus negative 5 is negative 6, so then we have negative 6, 2 plus negative 6 is negative 4, 1 times negative 4 is negative 4, 7 plus negative 4 is a positive 3. There's our remainder. And what? And your full answer, yes. So we're trying to like. It's kind of weird.
When you plugged in 1 for them, 1 minus 6 over here is that negative 5. Then minus the 1 is negative 6 plus the 2. So each step that you took up there is what you're writing down there. Does that make sense? So like 1 minus 6 is that negative 5. Minus the 1 is the negative 6. Plus 2 is the negative 4. Plus 7 is the remainder of 3. It's like they
yeah. Yeah, because it really does go like you start here, like you multiply here, and then you just keep going.
But it's also the same when you plug it in for them and then just do your regular addition.
Yeah.
As well.
Good call. Good point. It is the same. I like it. Good connections. See, this is what math is all about. Like seeing the connections, like being like, oh, there's the pattern. Like it's the glory of God right there. I love it. Okay, so then the factor theorem. All right. A binomial, so again, we're back at this binomial x minus a, is a factor of a polynomial p of x if and only if p of a equals 0. So if and only if p of a equals 0. Okay, because we know p of a is our remainder, right? That's what we just talked about up there. When we solve for p of a, this is our remainder. So if our remainder equals 0, then we know the binomial is a factor. Like you guys already know this. It's just worded in a different way to make it this theorem. Okay, so the factor theorem relates the zeros of a polynomial function and its factors. The factor theorem implies that a polynomial's linear factors, x minus a, can be found by finding the zeros or the roots of the polynomial function. 0 and roots are synonyms. Okay. So, example 2, determine whether x plus 2 is a factor of p of x equals x to the fourth plus 2x cubed plus 2x squared plus 3x minus 2. All right. So we want to keep trying this remainder theorem. Okay, giving you more tools in your toolbox. So with that being the case, here's our x plus 2. What is our a value? Okay, it's the -2, which is why it says to evaluate p of -2 to help us.
So what
We're finding the remainder still, but this time if what we're learning is if the remainder is 0, then this binomial is a factor.
So it's the same thing, just say if it's 0, it's not the same.
If it's 0, then it's a factor. Like on example 1, we didn't know that information yet. Example 1, the remainder was 3. So is x minus 1 a factor? No, exactly. So we're just building on that. We're going to do the remainder theorem.
So you're doing just the same thing. It's just saying, yes, if it's 0, it's a factor.
Correct. We're just saying PS, it's a factor or it's not a factor. You got it. Good call. All right, so we're going to do P of negative 2. So we're going to have negative 2 to the 4th plus 2 times negative 2 to the 3rd plus 2 times negative 2 squared plus 3 times negative 2 minus 2. So this one is not as nice as the 1, but we can remember if we have a negative number, anything to an even exponent is always going to be positive. If it's an odd exponent, it's going to be negative. So then it makes it a little bit easier. So we know this is going to be positive. 2 to the 4th is 16. Plus 2 times, it's to an odd exponent, so it's going to be negative. So what's 2 cubed?
So it's
8, because 2 times 2 times 2. Plus 2, so negative 2 is going to be squared. It's going to be a positive 4. Plus 3 times negative 2 is negative 6 minus 2. All right, so now we've got 16, 2 times negative 8 minus 16, plus 2 times 4 is 8, minus 6 minus 2. So even if you wanted, you could be like, okay, 16 and that minus 16, that cancels, and then say, well, 8 minus 6 is 2, 2 minus 2 is 0. So what does this remainder tell you? All right, so yes, this means that x plus 2, this quantity, is a factor.
And I'm assuming later we're going to figure out why that matters. Either Wednesday or after that.
Why being a factor matters?
Yeah, like you're going to do something with that.
Because we've kind of already learned why it matters. Like if it's not a factor, then it's not like a, I don't want to say a real division problem, but we wouldn't like to simplify a polynomial. Because remember how we simplified quadratics? Okay, so we're going to get polynomials. We're going to get to the place where we're going to simplify our polynomials, and we're going to end up getting a binomial, and we get a quadratic, and then we're going to go and simplify the quadratic, so we have the most simplified polynomial.
So basically you're learning to do this to figure out if we need to do more math to make it even simpler.
Yeah.
So basically if you divide it and you don't get 0, it's like, sorry, you didn't have to do that. But thanks anyway.
Yeah. You got it. You got it. I like it. We're going to make it a little bit easier to figure out if you're going to do it or not, or if it's going to be worth it, with the rational root theorem here. Okay, so the rational root theorem. Okay, so we've still got our polynomial, right? If polynomial, blah, 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 whatever. Okay, that we said, well, this is kind of what we've already been doing. Totally fine. So if we have polynomial is a polynomial function with integral coefficients. Okay, and p divided by q here is a rational 0 or root in simplest form. Okay, remember, the 0 or the root are synonyms. Okay, that's what we're looking for. That's when our remainder equals 0. Okay, all those things are the same thing. Okay, so what this means is p is a factor of the constant term, and q is a factor of the leading coefficient. Okay, so if we had, so here, this would, okay, so p is a factor of the constant term. So p is your constant. Okay, so if we look at this example, okay, negative 6 is our constant, so this is our p term. That's a good question.
They keep renaming it.
How can P be a factor of the constant term when P is the constant term?
Yeah, that's what I was about to ask. Like, if P isn't the constant term, it's a factor of the constant term, isn't it?
Well, it's always going to be a factor.
But because it's a constant, it is the constant term as well. Because it would be 1. Like 1 is your constant.
So you're just factoring it by or dividing it by itself.
Yes. And as far as like why they rename them, like polynomial is a capital P, this is a lowercase p. Yes, I agree. Because in a polynomial, it's called the, like it's still the constant term, but it's the P in this case. I got nothing. It's usually linked to Latin. Because a lot of math, like language, comes from Latin. So
why doesn't it say P is the constant term instead of saying P is a factor of the constant term? Why wouldn't it just say P is?
Because the constant term is technically A sub O.
But that is.
Which is the constant term.
But 6.
But P is the constant term.
Right. It is true. So
this doesn't make any sense.
You're analyzing the English at your level. At a higher level of math, there may be a different reason for that. But right now, like P is the constant term. Like whether they call it a factor of the constant term or it is the constant term. Later on, you might find a reason why they call it a factor of. I just can't explain it to you at this point. It is the constant term. Sorry about that.
Your face tells me it's not, but we're going to go with it is.
No, like it is. I don't know why that the book in this case says it is a factor of the constant term. Like, then go for it. Cross it out. I don't blame you.
So is it the same thing with Q is a factor of the leading coefficient if Q is the leading coefficient?
Yeah, Q is the leading coefficient.
So Q in that form would be 1.
So yes, here, because the leading coefficient, right, is always your first one. And so Q here would just be 1. We don't write it. So this is our Q term. So yes, you got it.
So you divide the first number by the last number.
Other way around, because it's P divided by Q.
So you divide the last number by the first number.
Yes. Okay, so here is the thing. The rational root theorem is not my favorite. Okay, but it is and it's not. Let's go with that. It's never my favorite, but it's okay. So the rational root theorem is going to generate a list of all the possible rational roots of a polynomial. So instead of you being like all willy-nilly about trying to pick, like if it says like find a root, like this one says factor P of X equals, it doesn't tell you what to divide by this time. You have to pick something. Yikes, where do I even begin? This sucks, right? Like, I like, can we go back a day where you just tell me to divide by this number and I'll do it? I don't care. I'll do long division and synthetic division. Just tell me what to divide by. That doesn't happen anymore. Now you have to figure out what to divide by. So this is why I like the rational root theorem, but sometimes it can go on forever. So what we do with the rational root theorem, okay, we make a list of all the possible rational zeros by listing, we're going to list the possible factors of the constant term and the leading coefficient. Remember, the constant is your P, the leading coefficient is your Q.
So in this case, we're going to be 1, 6, -6.
So it doesn't
Okay.
matter which one, you just have to pick one.
Nope, we have to list them both. So we're going to do factors of -6. Okay, I'm going to make this little T-chart over here. Because 1 and 6 get us 6, right? We good with that? But it also has to be a positive and a -1, and a positive and a -6. Because we're not talking just a positive 6 anymore. And even if we were, we're above, like it's not just 1 times 6. It's going to be a 1 times a -6 will give me -6, or a -1 times a positive 6. So these are plus and minus. The other factors of 6 would be plus or -2 and plus or -3. Okay, we understand why it's plus and negative? Positive and negative?
I thought you were dividing those numbers.
We do divide them in just a minute. So, just a second. So then we need to do the factors of 1. That says of. Which is just, yeah. So I'm just going to write them. Yep, it's the same one. So we're good. So now, okay, we're going to do the P over Q. And this is the reason. So these are our possible zeros. So our possible zeros, okay, are going to be the P divided by the Q and what those equal. Okay, so what is like, we have, we can write them out or we could just write the answers. What would you all prefer? Like, do you want to see the work or do you just want to see the answer?
I don't know.
Okay, so we're going to take a P. Oh, I don't want to set that there. Sorry. We're going to take our P value. These are up. Okay, so this, I'm going to write up here. This is P to keep us straight. These are the Q's. All right, so we're going to take the P and divide it by the Q. So no, we're going to take each P and divide by each Q. But thankfully, their Q, there's only one Q. So -1 or positive and -1 divided by positive or -1.
Those are just factors. Those aren't P themselves. Those are just factors.
That's why it said the factors.
Right. So
you're going to take the factor of the P and you're going to divide it by the
okay. So now I've got it. Here we go. Get back to this definition. P is a factor of the constant term. There it is. Because we have to factor it. And Q is a factor of the leading coefficient. So we had to factor them. And now we take the factors. That's why. So P is not 6 and P is not Q. P is the factors. So these are the P's. And
it shouldn't have said
these.
P is a factor. It should say P is the factors. Probably maybe a better way of.
Right. So these numbers are the P's and those are the Q's. Does that make sense? So now, see, now I know why the definition is written like that. Because before I'm like, I don't know. Like I knew we needed to factor it, but my brain wasn't making that connection.
What was like? Remember quite a while back where we had those like things of a 3 by 3, you multiply them like this.
Matrices. Mm-hmm.
That's what this reminds me of. When we have.
Oh.
Or like multiplying all by the other thing.
Gotcha.
There's no way we can put it into a matrix though.
No, it is not. Mm-mm. No.
Honestly kind of forgot how
it's kind of like boiling and just dividing everything by.
Yeah. Mm-hmm. Okay, so in that case, we do have to take each of these P's and divide it by the Q. And this one's nice because there's only one Q. So 1 divided by 1 is? Right, so it's positive or -1. 2 divided by 1 is?
It's just going to be all the P's.
It's just going to be all the P's in this case. You got it. So these are the possible zeros. Okay, so we've done really great work here. Now, so we got this little step out of the way. We need to evaluate the possible zeros of P of X to find a factor. So we need to know, like, well, which ones are the factors instead of doing all the math. So we're going to evaluate them. Yes.
That's exactly what we're going to do.
So that's why we learned this P of X thing. Okay, so we're going to do P of X. No, we want to find out which one. It depends on how you look at it. We want to know which. We want to find one that's 0. Yes. So we're going to start with.
You just plug them in and do the math and solve it.
Oh, I thought they all were the zeros.
No, these are possible zeros. So they give us some idea of where to go, but we still have 8 possible zeros. Right, but at least but we didn't put in 4 and try 4 or -4 or 5 and -5 and 20 and -20.
It's within this range, but we don't know within this range which one it is.
Right. So we're going to plug in, so we're going to have 1 cubed minus 3 times 1 squared plus 5 times 1 minus 6. They are just going to take a long time. Mm-hmm.
I understand what you're doing. Can I run the rest?
Yes. Mm-hmm. Okay, so 1 cubed is 1. 1 squared times negative 3 is negative 3. Plus 5 times 1 is 5. Minus 6. So 1 minus 3 plus 5 minus 6 is negative 3. So not a 0. So we're going to go to the next one.
Also, I would do a positive or a negative one because, I mean, I guess it could come out differently. I just figured it would be the opposite of without the plus. I guess like.
Okay. All right, so negative 1 cubed is negative 1. Negative 1 squared is 1. So negative 3 times 1 is still negative 3. Minus 5 minus 6.
Oh, wow, that's a big negative. Okay,
So that gives us negative 15, not a 0. You're like, oh, I got to keep going. Okay. So P of 2. So we're going to have 2 cubed minus 3 times 2 squared plus 5 times 2 minus 6. So 2 cubed is 8. 2 squared is 4 times negative 2, so minus 8. 5 times 2 is 10 minus 6. Hold on, wait. Nope. Oh, I forgot. This is 3. I wrote the wrong number. This is 3 times 2 squared, which is going to change this 8 here. So my bad. So 2 squared is 4. 4 times 3 is going to be negative 12. So 8 minus 12 is negative 4. Plus 10 is 0, or 6 minus 6 is 0. So it's like, woohoo! We have found a factor.
Yay! Do we have to find if there's any other factors?
Now we have to divide.
No.
There's the step. Yeah, because it said we have to factor it. So we found a factor. Now that we have a factor, we know what to divide by. Now we actually have to divide.
Okay.
But the good news is we can divide like it already has it. It's 2. Okay. Because this was our factor. It's 2. So then it's going to be 1, negative 3, 5, and negative 6. Yep, once you find the one factor. So 2 times 1 is 2, so negative 1, negative 2, 3, 6, and 0. See, no remainder. So now we have x squared, right? Thank you. Squared minus x, yep, and then plus 3. Times x, right? 2 is our factor, so x minus 2.
Why have to write times?
Ah, I moved the whole thing. Because we were we had to factor the polynomial. So once we found that 2 is a factor, that is equal to the binomial x minus 2. And then we divided it to find the other one.
That's how you write your answer.
This is how we write our answer. That should be fine to get you through tomorrow's. Like I said, tonight's homework says day 1 at the front, on the front. And then tomorrow you will be practicing. The worksheet is using this remainder theorem. Yes. So tomorrow you only have, you have a worksheet to work on all day in class. And if you find a remainder, then only then do you divide.